Welcome to the last installment of topics 3 and 4, posing the question, will two current-carrying wires attract or repel each other? If a magnetic field is in opposite directions, the wires will attract. In the same way, two magnets with opposite poles will attract. If the fields are in the same direction, the wires will repel. The electric motor uses this phenomena. It continuously rotates. Here in this case, the electrical current is going in the same direction. These two wires will repel. The electrical current is going in the opposite direction. These two magnets will attract each other, or two wires will attract each other. The wires will attract if the magnetic fields are in opposite directions where they overlap. They will repel if they are not. A simple DC motor converts electrical energy into mechanical energy. What makes up a motor? It has to have an armature. So here's your armature, which is a loop of wire. It has to have a commutator, which provides electrical contact so the current can reach the coil of wire. It also has to have a brush to make contact. So here's the brush, and a power source. How does a motor work? As the current flows through the coil, a magnetic field is generated. This is an induced magnetic field. The induced magnetic field generated by the coil will be attracted to the poles of the permanent magnet. So this will cause the magnet to turn. The armature can be connected to the blades that turn. So the armature can be connected to, for instance, a blow dryer or a fan or something like that. Since electron flow produces a magnetic field, can moving a magnet produce electricity? The answer is, of course, yes. This forms the basis of generators. Generators were used to be called dynamos. Generators are the opposite of a motor. Generators convert mechanical energy into electrical energy. Electrical induction occurs when a moving magnet, in this case, the rotation of a coil produces a current. The current produced is an alternating current, or AC. So here you have the magnet. As you move the magnet, it induces a current. When the magnet changes the direction, the current also changes direction. So as you go up and down, the current also changes direction. Direct current generator is impractical because it would require large and heavy magnets. Modern generators turn a coil of wire in a permanent magnetic field. The motion of the conductor in a magnetic field induces a current. Can current be induced in a second coil near a coil carrying direct current? Yes, it can. This is called a transformer. So you have a primary circuit and a secondary circuit. We depend on electricity. The power lines coming into our house every day carry alternating current. However, the voltage carried in power lines is too high for most. For most household appliances. Transformers change the voltage of electrical energy supply. They may be step up, so they may increase the power, for instance at a generating plant, or step down, decrease the power for home. This allows for power transmission over long distances, but energy is still lost during long transmissions. So those are all examples of transformers. However, they're not the same transformers that we're talking about. Metering current transformers and voltage transformers are two types of transformers. Transformers have an iron core. They have a primary coil or input voltage, and they have a secondary coil or output voltage. So a transformer transforms AC voltage of one current to a different AC voltage in another circuit using separate coils of wire wrapped around an iron core. How does current move from the primary to the secondary coil? Due to the changing magnetic field produced by the primary coil and concentrated by the iron core, you get electric field induced in your coil of wire. Why AC instead of DC? Since power is equal to current times voltage, transmitting power at a safe low voltage requires a large amount of current. But transmitting a large current results in lines becoming heated. This means a large energy loss. At the site of power generation, the transformer steps up the voltage. At the site of use, the transformer steps down the voltage. Long distance transmissions are now safe. Transformers. A step-up transformer, the voltage is increased. There are more secondary coils than primary coils. In a step-down transformer, the voltage is decreased, so there are less secondary coils and more primary coils. Both change the voltage of an electrical energy supply. Protection from electricity. Whenever your body becomes a short circuit for electricity, you have the potential to get electrocuted or shocked. This can be dangerous. Fuses, circuit breakers, and polarized plugs are designed to protect us. Fuses are placed in series in a circuit. If a current is high, fuses conductors overheat and melts. The circuit is then broken. Uses a conductive material with a low melting point, narrow cross section, and less conductive material. Circuit breakers open the circuits automatically if the current becomes too high. They are found in fuse boxes in the basements of homes. If the wiring is rated at 15 amps, circuit breakers must be 15 amps. If the current rises above this, the breaker trips and the circuit is broken. Without a breaker, a wire could overheat and your house could catch on fire. Ground fault interrupters are found in bathrooms and in hot tubs. Anywhere where humidity has the potential to become very high. It could also be found in your kitchen. A Class A ground fault interrupter opens when conditions suggest a person may be drawing 6 milliamps. 6 milliamps is the safe maximum human exposure to a current at 100 volts. Anything higher than this can cause electric shock.